the beginning, the AMCA is organized by MAA. It's 25 questions long. It's 40 minutes, and on average you get 1.6 minutes per question. It's multiple choice, and there's no negative marking. And your score is just the number of questions you get correct. And there's no lower grade limit, so anyone in grade 8 or lower can take it. Even elementary schoolers can take it. The competition date is mid-November, typically, but next year it might change, and the AMC 8 might move to February, and the AMC 10 might move to November. Okay. So now let's take a look at some important numbers that you should know. The prime factorization of 2020 is 2 squared times 5 times 101. There are 12 positive integer factors of 2020. The factors of 2020, this is really optional, you don't really need to know this, but it may be helpful to know the factors of 2020. The prime factorization of 2019 is 3 times 673, and the prime factorization of 2021 is 43 times 47. So in general, whenever you're taking a certain year's competition, you should always memorize the prime factorization of that year. Okay, so now let's take a quick review of some of the important combinatorics topics. So, a factorial and factorial is just n times n minus 1, times n minus 2, all the way till times 1. And the number of ways of arranging n objects in a line is just n factorial. And the number of ways of arranging n objects in a circle is just n minus 1 factorial, where rotations are considered the same. And a quick review of the word rearrangements. So the number of ways to rearrange the letters in a word is just n factorial over the d1 factorial, d2 factorial, d3 factorial, so on, where d1, d2, d3, those are the number of times, those are the number of duplicates. So the number of times each of the letters that appear more than once come. So as a quick example, how many ways to arrange the letters in the word review? Well, the way I like to do it is I like to write them in a way where you can see all duplicates. So you can see that, okay, R, E, V, I, E, W. There are a total of 6 letters, so 6 factorial, divided by, there's 2 E's, so you divide by 2 factorial. This gives you 360. 720 divided by 2, or 360. Okay, so now let's take a look at permutations. Permutations, the formula for assigning the number of ways of assigning k's positions to n distinct things is n factorial over n minus k factorial. And as we'll discuss in the next slide, usually the words permute or doesn't matter, etc. imply a permutation. But then for combinations, so the difference between permutations and combinations is combinations are where you're choosing k distinct objects from n objects, or you're sending k of the same positions to n different things. And in permutations, the order of the k objects matters. In combinations, the order does not matter. So that's the key difference. And the combination formula, n choose k, is just n factorial over k factorial over n minus k factorial. And this is also a fact you may want to know. And usually the words choose, select, order doesn't matter, etc. imply that you should probably use the combination. And some strategies here. Casework. Casework is when you solve problems by considering the different cases and adding them together. Complementary counting is when you count the opposite of what you want and you subtract it from the total number of cases. And remember, when you see at least, that's a sign of complementary counting. That's a thing that you should probably want to use complementary counting most of the time. So let's try a quick example here. If Fred's bank is composed of 4 digits from 0 to 9, with repeated digits allowable. If no password may begin with the sequence 911, how many passwords are possible? So firstly, let's find the total number of passwords. There are 4 digits. Each digit can be from 0 to 9. Right? So there's 10 choices for each of the digits. So 10 times 10 times 10 times 10, which is 10,000. And then we must also subtract off some passwords that are not allowed. So for example, 911. So we have to subtract the passwords that start with 911, since those aren't allowed. And how many passwords start with 911? Well, if they start with 911, there's 10 choices for the last digit. The last digit can be anything from 0 to 9. So there's 10 choices for the last digit. So there are 10 ways that don't work, that start with 911. And there are 10,000 total ways total possible 4-digit passcodes. So overall, the number of passcodes is just going to be equal to 10,000 minus 10 equal to 9990. This is our final answer for this problem. Now let's take a look at overcounting, the process of counting more than what you need, and then systematically removing the parts that do not belong. How many positive integers less than 1,000 are multiples of 2, 3, or 5? Okay, so firstly, how many multiples of 2 are there? There are 1,000 divided by 2 equal to 500 multiples of 2. There are 1,000 divided by 3 equal to 333 multiples of 3. There are 1,000 divided by 5 equal to 200 multiples of 5. Except we're overcounting some. Like I said earlier, we must systematically remove the parts that don't belong. So we must remove the parts that are extra, that don't belong here. So we must remove the multiples of 2 and 3, the multiples, so how many numbers are multiples of both 2 and 3? Well, there's going to be 1,000 divided by 6 equal to 166 of those numbers. Right, because when we're counting the multiples of 2, 3, and 5, we're overcounting the multiples of 2 and 3. Because they're counted as part of the multiples of 2 and multiples of 3. And then we must also subtract the multiples of 3 and 5. So 1,000 divided by 15, which is 66. And then we must also subtract the multiples of 2 and 5. Because the multiples of 10 or the multiples of 10. Because those again are being overcounted. So minus 1,000 divided by 10 equal to 100. So overall, there are a total of 1,033 possibilities here. 1,033 multiples of 2, 3, or 5, except we overcounted 332 multiples that we overcounted them. Except, there's still one thing that we're missing here. The thing that we're missing now is that there's some numbers that are multiples of 2, 3, and 5, or multiples of 30. So the multiples of 30 are counted as part of the multiples of 2, as part of the multiples of 3, and as part of the multiples of 5 in the beginning. But then, they're also subtracted as part of the multiples of 6, multiples of 15, and multiples of 10. So now, we're not counting the multiples of 30 at all. We're not counting them, we're counting the multiples of 30 0 times. So therefore, we must add back the number of multiples of 30, which is just going to be equal to 33. So overall, we just do 1,033 minus 332, which is 701, plus 33, which is 734, which is our answer. Okay, so now let's take a look at probability. Probability is the likelihood of something happening, and it's just the total successful outcomes over the total possible outcomes. And in general, you can use methods of casework and complementary counting to find the total number of successful outcomes. And there's also combinatorics for grid problems. So the formula for the number of squares of all sizes in an n by n grid is 1 squared plus 2 squared plus 3 squared all the way till n squared. Or n times n plus 1 times 2n plus 1 by 6. So in a 4 by 4 grid, the number of squares is just going to be equal to, in this 4 by 4 grid is just going to be 1 squared plus 2 squared plus 3 squared plus 4 squared. The reason for this is because there are 1 squared of the 4 by 4 squares, there's 2 squared of the 3 by 3 squares, there's 3 squared 2 by 2 squares, and there's 4 squared or 16 of the 1 by 1 squares. The general formula for the number of rectangles of all sizes in a grid is n plus 1 choose 2 times n plus 1 choose 2. This actually is really clever. The reason this is true is because there's going to be n plus 1 horizontal lines and an n plus 1 vertical lines. And in order to get a rectangle, we must choose 2 horizontal lines and 2 vertical lines. So just to demonstrate, if we choose 2 horizontal lines like this, let me just draw. So we have 2 horizontal lines like that. And then we choose 2 vertical lines like this. a rectangle, or even a square would be counted as part of the rectangles, is formed at the center. So in general, that's how the formula comes. And the number of ways to get from 0, 0 to xy on a coordinate plane, where you can only move right and up along the grid lines, is x if I choose x. So for example, the number of ways to get from 0, 0 to 4, 4, you just 4 plus 4, choose 4, or 8 choose 4, which is 70. Okay, so now let's take a look at recursion. So for recursion problems, you always start at the first step and try to define subsequent steps in terms of the first step. So for recursion problems, for example, what you do is you define some function f, maybe, let's say, okay, let's say you want to find how many ways to do something for n equals to 12, some really large number. So the idea was you just say, how many ways to do it for the 0, if there's 0 of them, so f of 0. Then you find f of 1. So on, you keep finding these small values. And then in order to get the larger values, in the beginning you find some small values, and then you iteratively calculate the larger values. So maybe you're going to get some relation that, okay, maybe you found that f of 2 is equal to f of 1 plus f of 0. And then maybe you have f of 3 equal to f of 2 plus f of 1. And you can repeat this process all the way to get f of 12. And then you get it equal to some number. So in general, this technique is extremely powerful, and it can help simplify a lot. And I know I didn't explain too many details here. For more details, you can check out one of the classes I taught earlier. Also, another formula that's very important, or technique, is stars and bars, or also known as sixteenth zones. So basically, whenever you have n objects, or n stars, as the names come from, and you have k, you want to distribute these n objects to k things. You place n minus 1 bars in these k things to get that there are n plus k minus 1, choose n ways to rearrange all the objects in this line. And use stars and bars whenever you're distributing identical objects to people or groups. Okay. So, but again, I don't recommend just memorizing this formula and not knowing how to actually get the formula, because sometimes the problem can give variations. So it's important to know that you place how do you place the bars and how many ways to arrange them from there. So let's try an example here. We have 10 cookies, and you want to give the cookies to 4 children. So we have 10 cookies, and since we want to give them to 4 children, there's one extra condition. Every child gets at least 1 cookie. So what can we do about this? Well, we can just designate 1 cookie per child. So you can just say child 1 gets the first cookie, child 2 gets the second cookie, child 3 gets the third cookie, and child 4 gets the fourth cookie. And then there are 6 cookies left. And these 6 cookies you must distribute to 4 children. And how many ways are there to distribute 6 cookies to 4 children? Well, in order to count that, we just place 3 bars in between. So we place 1, 2, 3. You can place them anywhere. And how many ways are there to arrange this? That's just going to be 9, 2, 3, or 84. Okay, so now let's take a look at algebra. So mean, median, mode. Mean is the average of all the numbers. Mode is the most common number. And know that there could be multiple modes, but if the problem says unique mode, it means that there's only one mode. After arranging all the numbers in increasing to decreasing order, if the number of terms is odd, the median is just the middle number. If the number of terms is even, the median is the average of the 2 middle numbers. And I've only seen harmonic mean ever come up on one AMC problem, but you can memorize it if you want. It's not that important, so I'm not going to go for it right now. And there's going to be handouts that I'll send all to all of you after class, where you can review all the formulas and all the techniques to solve AMC problems. And also sometimes you see graph problems, and they're usually not that hard. They're usually just basic applications. So the best way to solve them is just to carefully analyze the graphs and eliminate some answer choices. And usually they'll be somewhere from number 1 to 15, so they won't be that hard, and they'll generally be pretty easy to solve. Okay, so telescoping is another extremely nice topic. So for telescoping, you want to expand the first, few, and last terms and cancel out any terms you see. Okay, so let's try going over this, how to solve this problem. This problem is tricky, so let's see what we can do. 1 over 2 times 3 plus 1 over 3 times 4 all the way to 1 over 99 times 100. And if you actually try adding them, that would be almost impossible. 1 over 6 plus 1 over 12 plus 1 over 20 plus 1 over 9900. I mean, there doesn't really seem to be a way that we can somehow telescope this sequence. So the idea here is to see that, well, we have 1 over 2 times 3, 1 over 3 times 4. Let's expand term by term. Let's not write the whole sequence before we don't know how to handle it yet. So what's 1 over 2 times 3? That's just going to be equal to 1 over 6. And 1 over 6 is equal to 1/2 minus 1/3. So if you know that 1/2 is 3/6 and 1/3 is 2/6, you might see that 1/6 is equal to 1/2 minus 1/3. Similarly, 1 over 3 times 4 is equal to 1/12, which is equal to 1/3 or 4/12 minus 1/4 or 3 over 12, which is 1 over 12. And so on. We can continue writing terms from the sequence. So 1 over 4 times 5 will be 1 over 4 minus 1 over 5. So now let's see, and in general, if you have 1 over n times n plus 1, it's going to be equal to 1 over n minus 1 over n plus 1. Okay, so as you can see here, that means that this whole sequence will telescope. So then the sequence can be rewritten as 1/2 minus 1/2 minus 1/3 plus 1/3 minus 1/4 plus 1/4 minus 1/5, so on, dot dot dot, all the way till plus 1 over 99 minus 1 over 100. And as you can see here, the 1/3 terms will cancel, the 1/4 terms will cancel, and so on. The 1/5 terms will cancel, the 1/6 terms, all the way to the 1 over 99 terms will cancel. And we're left with just 1/2 minus 1 over 100. Is equal to, which is just going to be equal to 50 over 100 minus 1 over 100, which is 49 over 100. Which is our answer for this problem. Okay, so now let's take a look at speed, distance, and time. Distance is equal to speed times time. Speed is equal to distance divided by time. And the average speed is the total distance divided by the total time. And another useful factorization is difference of squares. A squared minus b squared is a minus b times a plus b. And for systems of equations, the idea is to set up an equation and let any unknowns be variables. So for example, in this problem, we have, starting with some gold coins and some empty treasure chests. I tried to put 9 coins in each treasure chest. But then 2 treasure chests are left empty. So immediately, right off the bat, we see that there are 2 unknowns. The amount of coins. So let's see, there's T coins, and there's T chests. So then, if you try to put 9 coins in each chest, there are 2 treasure chests empty. The amount of coins will be equal to 9 in each chest times T minus 2 treasure chests that we're actually using. But then we also see that later, instead, he put 6 gold coins in each chest, but then there's 3 gold coins left over. So then the number of coins is equal to 6t plus 3. But then we know that 9t minus 2 is equal to 6t plus 3. So that means that 9t minus 18 is equal to 6t plus 3, meaning that 3t is 21, or t equal to 7. And if t is equal to 7, then the number of coins is just going to be 9 times 7 minus 2, or 45. So 45 is our answer. And a good way to check your work would be to see that, okay, we can just plug it into our second equation. And that's just going to be 6 times 7 plus 3, which is also 45. So therefore we can confirm our answer is correct. And make sure to stay till the end, because later we're going to discuss many different problem solving strategies and how to actually get the answer without actually solving the problems. So those are some strategies that can really help when you don't know how to solve it, but you can still get the correct answer. So next we're going to talk about arithmetic sequences. An arithmetic sequence is a sequence where we have the same difference between consecutive terms. So in this sequence we add 3 each time. And these terms can be represented as a1 through an, where n is the number of terms and d is the common difference. The formula for the nth term in the arithmetic sequence is right here, as you can see. And a more general form is an is equal to an plus n minus n times d. Another very useful formula is that the number of terms in the arithmetic sequence is the last term minus the first term over the common difference plus 1. It can also be written like this. The average of terms in arithmetic sequence is just the first term plus the last term by 2. Or it can also be written like this. And the average is also just the sum of all terms divided by the number of terms, which is just this. And if the number of terms is odd, the average of terms is just the middle term. And if the number of terms is even, the average is the average of the 2 middle terms. And the sum of all terms in arithmetic sequence is just the average of all terms times the number of terms. And when you substitute our expression, we can get another formula for the sum. And some very important special arithmetic sequences are that the sum of the first n numbers is 1 plus 2 plus 3 plus 4 all the way till n equal to n times n plus 1 divided by 2. Sum of the first n odd numbers is 1 plus 3 plus blah 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 all the way till 2n plus 1 is going to be n squared. And again, I talked about this more detailedly in one of my previous classes, where we did many examples as well. So next we're going to talk about geometric sequences. This is where you have the same ratio between consecutive terms. For example, in this sequence, we multiply by 2 each time. And in general, the terms are a1 through an. N is the number of terms, r is the common ratio between terms. And then the nth term in a geometric sequence is the first term times r to the n minus 1, or in the more general form is there. And the sum of a geometric sequence. Okay, so the sum of a geometric sequence is going to be the first term times r to the n minus 1 minus 1 divided by r minus 1. If r is greater than 1, and if r is less than 1, it's going to be a1 times 1 minus r to the n minus 1 over 1 minus r. And if you notice, these expressions are the same thing, except that we can avoid negatives when we use the different forms. So we don't have to deal with negative numbers. The sum of the terms in a geometric sequence, infinite geometric sequence, where the ratio is less than 1, is a or the first term, divided by 1 minus r, the common ratio. Okay, so now let's take an example. This problem was actually intended to be in the competition tomorrow, but it ended up not being used, so I decided to put it in today's class. Two arithmetic sequences have first terms of 11 and 13 respectively. The common difference in the first term is d, whereas the common difference in the second term in the sequence is 2d. The sum of the 23rd terms of both sequences is 222. Find d. Okay, so if two arithmetic sequences have first terms of 11 and 13, well then what is the 23rd term? In the first arithmetic sequence, the 23rd term is going to be 11 plus 22d. The second term is going to be equal to 13 plus, well, there's 22 common differences, and each common difference is 2d, so plus 44d. And the sum of both of these is 222. So the sum, 24 plus 6060, is 222, which means 6060 equal to 198. And what does that mean? Well, we can just divide by 66 from both sides to get that d equal to 3. So now let's take a look at number theory. Okay, so primes are numbers that have exactly two factors, 1 and itself. And for example, these are all prime numbers. And make sure to remember that 1 is not prime. And again, prime factorization, you probably already know this, but let me just quickly go through it, is how we can express numbers as the product of primes. So 21 is 3 times 7, for example. 60 is 2 squared times 3 times 5. And a number with prime factorization, p1 to the e1 times p2 to the e2, all the way till times pk to the ek, has e1 plus 1 times e2 plus 1, all the way till ek plus 1 factors. And basically, in order to find the number of factors of a number, you find the prime factorization of the number, you add 1 to all the exponents, and you multiply those all together. And this is very, very useful, and it can tremendously simplify finding the number of factors. Okay, so now let's take a look at divisibility rules. So a number will be divisible by 2 if the last digit is even. If a number will be divisible by 3 if the sum of digits is divisible by 3. A number will be divisible by 4 if the last two digits are divisible by 4. So for example, if you have a number 98624, it's going to be divisible by 4 since the last two digits are divisible by 4. A number will be divisible by 5, the last digit is 0 or 5. A number will be divisible by 6 if it's divisible by about 2 and 3, which you can check from the divisibility rules. And for 7, there's a divisibility rule, but I never have memorized it, so what I do is it's really complicated, the divisibility rule for 7. What I do is I just take out factors of 7 until I get a number that's either divisible or not divisible by 7. For example, 105. What I can do is I can take out 70, because I know 70 is 7 times 10, and I get 35. But from 35, I can take out 35, because I know 35 is a multiple of 7, and I get 0. And since 0 is divisible by 7, so is 105. Well, now let's take a number that's not divisible by 7, so maybe 108, for example. For 108, what we can do is we can take out, again, 70, we get 38. And we can take out 35, because we know that's divisible by 7, to get 3. And since 3 is not divisible by 7, 108 is also not divisible by 7. This trick also works for other numbers, not necessarily just 7. It can work for any number. But for 7, there's not really a good trick, so that's why I'm using this method. And for 8, the last 3 digits have to be divisible by 8. For 9, the sum of the digits have to be divisible by 9. For 10, the last digit obviously just has to be 0. For 11, okay, 11 is a slightly more tricky one again. So for example, if we take the number 14641, so what we do to find whether this number is divisible by 11 or not is we number the digits. So this is the first digit, second digit, third, fourth, and fifth digit. So we find the sum of the odd number digits and the even number digits, not the odd and even actual digits. So the odd number digits are the first digit, third digit, and fifth digit. So 1 plus 6 plus 1. Odd sum is equal to 8. The even sum is going to be equal to the sum of the second digits and fourth digit, which is going to be 4 plus 4, or 8. And then we take the absolute value of the difference. So we take odd minus even, so 8 minus 8 equal to 0. And since 0 is divisible by 11, so is 14641. And in fact, this is also really useful. It can also be useful for numbers that are not divisible by 11. And it can even work for even larger numbers, because that can be very time-taking if you're just trying to do it for other numbers. So for example, let's take another number, maybe like 122. The odd number digits are going to be 1 and 2, so odd sum is 1 plus 2. The even sum is just going to be 2, second digit. The difference, odd minus even, is going to be 3 minus 2, which is 1. And 1 is not divisible by 11. So therefore, 122 is not divisible by 11 either. And for 12, the number just has to be divisible by both 3 and 4. And for 15, the number has to be divisible by both 3 and 5. because 15 is just 3 times 5, and 12 is just 3 times 4. Okay, so modular arithmetic. When given different remainder conditions, we want to find how much more or less of a certain multiple each statement means and combine them together. What are the smallest positive number that leaves a remainder of 3 when divided by 5, 1 when divided by 3, and 4 when divided by 6? So 3 more than a multiple of 5, 1 more than a multiple of 3, and it's going to be 4 more than a multiple of 6. So from here, this seems like very strange. How can we possibly solve this? And as I discussed in one of the previous classes I taught, what we do is we look at the difference between the multiples. So this condition means that the number is 2 less than a multiple of 5. This condition means the number is 2 less than a multiple of 3. And this condition means the number is 2 less than a multiple of 6. But we see that if a number is 2 less than a multiple of 3, it's also 2 less than a multiple of 6. So this condition already implies this condition is true. Because if a number is 2 less than a multiple of 6, we already know it's going to be 2 less than a multiple of 3. Therefore, this condition is redundant. We don't need it, because it's already part of the third condition. So now the problem just becomes the first and the third condition left. That means that we know it's 2 less than a multiple of 5, 2 less than a multiple of 6. So that means it's going to be 2 less than a multiple of 30. And what does that mean? We want to find the smallest positive number that's 2 less than a multiple of 30. That's just going to be 30 minus 2, or 28. Okay, so now let's take a look at digit cycles. Digit cycles, the idea is just to take the first 2 values and look for a pattern. So for example, if you want to find 3 to the 1997, what you do is you find, okay, 3 to the 0 is equal to the unit digit of 3 to the 1997. Sorry, forgot to mention that. 3 to the 0 is 1, 3 to the 1 is 3, 3 squared is 9, and 3 cubed is just going to be 9 times 3, or 7, the unit digit, 7. And 3 to the 4 is going to be 7 times 3, or 1. And then the pattern repeats. So it repeats every 4 digits. It becomes 1397, 1397, so on. Keep repeating. So therefore, 3 to the 1997 is just going to be equal to 3 to the 3, the unit digit, which is 7. The reason that these are going to be equal is because every multiple of 4 recycle. And other very important facts are that the greatest common multiple of m and n, or the GCD, can be found taking the lowest prime exponents from m and n. And the LCM, or least common multiple, can be found by taking the highest prime exponents from both m and n. So we had a number m equal to 2 to the 5 times 3 to the 4, and n equal to 2 to the 6 times 3 squared. The GCD would just be taking the lowest exponents, 5 and 2. And the LCM, we would just take the highest exponent, so 6 and 4. Another cool fact is that GCD of m and n times LCM of m and n is equal to m times n. So the reason that this is true is because when we multiply the m and n, we're just multiplying both factors of powers of 2 and both powers of 3. But when we multiply the GCD of m and n and the LCM of m and n, we get n. The reason is that we're anyways taking both powers of 2 in the GCD and LCM, and we're anyways taking both powers of 3 in the GCD and LCM. So this will always be true as a result. Okay, so now let's try a problem. Which of the following integers cannot be written as the sum of 4 consecutive odd integers? So an odd integer can be represented in the form 2n plus 1, right? Because if it's 2n plus 1, it's going to be 1 more than a multiple of 2, or odd. Or maybe even 2n plus 3, 2n plus 5, or 2n plus 7. And we want These are all 4 consecutive odd integers. And we want to find which of these numbers cannot be written as the sum of these numbers, for example. So what you can do is when you add these together, you get, there's 4 2n's, you get 8n plus 1 plus 3 plus 5 plus 7, which is just going to be equal to 16. So what you might notice here is that this number is always a multiple of 8. So we want to find the number that cannot be written in this form. So we want to find the number that's not a multiple of 8. So clearly 16 is a multiple of 8, 40 is a multiple of 8, 72 is a multiple of 8, 200 is a multiple of 8, but 100 is not a multiple of 8. Okay, so if 100 is not a multiple of 8, then clearly it cannot be written in this form, so 100 must be the answer. And even though I used 2n plus 1 till 2n plus 7, sometimes it might even been easier to use 2n minus 3, 2n minus 1, 2n plus 1, and 2n plus 3. Because then when you use these 4 numbers, now they cancel out and they just equal to 8n. And again, these are also all consecutive odd integers. But both ways work fine, but this way has a little bit easier for solving it. Also, in addition, there's a way to solve this, get the answer to this problem without actually solving it. So you can do that by, for example, so the way you could solve this problem, get the answer to this problem without actually solving it, is you could see that, okay, the four numbers sum to each of these values. Let's find the average of the numbers must be. So if the sum is 16, the average must just be 16 divided by 4 or 4. If the sum is 40, the average must be 40 divided by 4 or 10. If the sum is 72, the average must be 72 divided by 4 or 18. If the sum is 100, the average must be 100 divided by 4 or 25. The average is 200, that is just going to be 200 divided by 5 or 50. Sorry, 200 divided by 4 or 50. And what do you notice here? This is even, this is even, this is even, this is even. So what's the odd one out? 25. So 100 is the answer. It is correct, as you saw here. We actually found that 100 can't be 8n. And this is just a way to, this is not the proper way to solve it. This is just a way to solve it if you don't know how to solve the problem yourself, or you don't have enough time. And this can be very useful, because another trick is that if you have the odd one out, it's very likely going to be the answer. So that's another good trick to keep in mind. That we'll actually discuss at the end more, about these kind of strategies to get the answer without actually solving it. Okay, so now let's take a look at geometry. So in geometry, we have that Pythagorean theorem, a squared plus b squared is c squared, in a right triangle, with sides a, b, and c. And a Pythagorean triple is just 3 numbers that satisfy the Pythagorean theorem. Okay, so these are all some very, very common Pythagorean triples that's definitely worth knowing. It can improve your speed, especially since on the AMC 8, that it can be very, very useful. Okay, and Pythagorean triples. And some Pythagorean triples, 3, 4, 5, 5, 12, 13, 7, 24, 25, 8, 15, 17. These are important. I highly recommend memorizing them. And some other Pythagorean triples that so Pythagorean theorem here, and some other important facts are that 3, 4, 5, 6, 8, 10, 9, 12, 15, so on. So when you multiply by 2 here, it's another Pythagorean triple. When you multiply by 3 here, it's another Pythagorean triple. When you multiply by 4 here, it's another Pythagorean triple. And when you multiply by 5, so on. Whenever you multiply by any constant to all the numbers, it's going to be a Pythagorean triple. And that works for other Pythagorean triples too. So if you have 5, 12, 13, for example, you multiply by 5. If you multiply by 5 to all terms, you get 25, 60, 65. This is also another Pythagorean triple. So you multiply by another number, let's say 7, 24, 25. and you multiply by another constant, you get more Pythagorean triples. So 14, 48, 50. Okay, so now that we've gone over Pythagorean triples and combinatorics, now let's take a short break for a few minutes. A form will be sent in the chat for any of you who want the copy of this handout after class. In order for me to email, I can email you the handout afterwards after class. And please fill out the form that will be put in the chat. So a form should be sent out in the chat. Okay, so now let's continue. So I'm sure most of you already know this, that the area of a triangle is base times height divided by 2. And the reason that this is true is because you can just construct a rectangle around the triangle. Just construct a rectangle on the triangle, and the area of a rectangle is base times height. The area of the triangle is just going to be half that area. The area of an equilateral triangle is going to be root 3 times 4 side squared. And we can actually figure out why this is true by using 30, 60, 90 triangles. So we can divide this up into two 30, 60, 90 triangles. And if you remember from 30, 60, 90 triangles, this will be, if this is S, this will be S by 2. And then this will be S root 3 by 2. And then the area of this whole triangle is just going to be 2 times, because there's 2 of these triangles, times 1/2 times S by 2 times S square root 3 by 2. And the 1/2 and 2 cancel out. We get S2S will become S squared root 3 by 4. And that's the formula for equilateral triangle area. And the area of a rectangle is just the base times the height. The area of a trapezoid is the sum of the bases divided by 2 times the height. The average of the bases times the height. And we can just divide it up into some triangles. Divide it into triangles, and then we can see the area will just be total. The total will just, the sum of these two bases is going to be b2 minus b1. And this is going to be h. So overall, we have that the area of this trapezoid is going to be b1h plus sum of those two bases, which is b2 minus b1 times h divided by 2, since it's a triangle. So b2 minus b1 divided by 2 times h. And we can add this up. When we add this up, we get equal to, we can take, it's just going to be equal to b1 plus b2 minus b1 divided by 2, which is b1 plus b2 divided by 2, and that's going to be the area of the trapezoid. Because now, this is something I actually didn't talk about in one of my classes, is that the area of a rhombus is d1, d2 divided by 2. The sum product of the diagonals divided by 2. And the reason this is true is because we can imagine extending, these lines. Sorry about that. Draw this line. Sorry, it's not a very good diagram, but the point is that you can imagine that there's 4 different triangles here, and the triangles are all going to have the two side lengths of d2 by 2 and d1 by 2, and then the area is just going to be 4 times d1 over 2, 1/2 times d1 by 2 times d2 by 2, and then these two will cancel with the 4, and we'll just be left with d1 times d2 divided by 2, which is the formula. In the parallelogram, the area is just going to be equal to the base times the height. The base is b, the height is h, and remember, the height always makes a 90-degree angle. So if I give you a parallelogram like this, if you have a parallelogram like this, find the area of this parallelogram if this is 5 and this is 7, for example. So for this, a very common mistake is just to multiply 7 times 5 and get 35, but then that's actually not true. So if we're given that the height is 4 and makes a 90-degree angle here, the height makes a 90-degree angle on the base. Make sure you remember that. And the height does not necessarily have to be inside. If you extend this line and we meet it, we have a 90-degree angle here. So the area of the parallelogram is just going to be equal to 7 times 4, which is 28. And again, the reason that this is true is because we can imagine that we can construct 2 triangles on both sides. We can construct a triangle there, a triangle there. And then we can draw this out. And the area of this parallelogram, well, in order to find the area of this parallelogram, what we can do is you can just, if this is x, this is x. The total area of this whole shape I just made is going to be h times b plus x. That's the total area of the whole shape. And then we subtract the area of the 2 triangles. So we subtract bx, or hx by 2, subtract hx by 2 minus hx by 2 to get this equal to hb plus hx minus hx by 2 minus hx by 2. So those will cancel out. These will all cancel. And it's left with equal to hb. And also the area of a circle is pi r squared. And the circumference of a circle is 2 pi r. And the reason the area of a circle is pi r squared is what you can do is if you have a circle, you can imagine splitting it up into infinitely small arcs. Many infinitely small arcs. And then they actually form a rectangle. They form a rectangle like this if we meant to bring the arcs together. they actually form a rectangle. So on, they form a rectangle with a base of the actual pi r, and then the height of a radius. So the area of the circle, to construct into a rectangle, is just going to be pi r, half the circumference, times r, which is pi r squared. And if you have arcs of a circle, the area of a sector is just going to be pi r squared times a over 360, where a is the angle it forms at the center over here. So a is the angle here. And the reason, again, this is true is because we have a sector, so it's just going to be a fractional part of the whole area. And same thing for the circumference, or length of the arc. 2 pi r times a over 360. And again, for these types of problems, for finding the areas of complex shapes, the idea is to extend lines, break up areas, look for nicer areas, because that can really help you. That can really help you find the different areas of it. And so, for example, I remember I did one of these. I've seen many AMC problems like this before, where they give a weird shape like this, for example, and you want to find the area of the shape. And the idea of finding these areas of these types of shapes is to actually extend lines. And then when you extend lines, you can get different arcs to form, and you can subtract off of those areas. So whenever you extend lines, it can always help. Because if you have some shapes inside, when you extend the lines, now you have 4 new shapes that you can subtract off sometimes. Okay, so also some other strategies are, if you have some complex shapes that you have drawn that they give you, you can break it up into some different areas and find the area of those individual pieces. Because if you find the area of the individual pieces, you can find the overall area of the whole thing. And also sometimes you look for nicer areas, so areas that are easier to work with. So maybe a square, an arc, a triangle, equilateral triangle, whatever we have, we can always look for nicer areas. And finding lengths of complex shapes, well, to do this, what we would do is we would say equal lengths, look for equal lengths, isosceles triangles. So if you have isosceles triangles, that probably means, oh, equal lengths, and then from there you can maybe use that to your advantage. And then this is something that's very, very useful, that I remember seeing a problem last year's AMCA, that was that you have a triangle like that, and this is 3, this is 4, and this is 90 degrees here. And you want to find the area of the shape. So the idea here for this problem that was actually on last year's AMCA was, see, okay, we have a 90-degree angle, we want to always use Pythagorean theorem. So whenever we see 90 degrees, somehow we have to use Pythagorean theorem. If you don't know how, try to figure out how. So since there was a 90-degree angle here, that immediately clued to everyone that, okay, Pythagorean theorem has to somehow be used here. So then in order to use Pythagorean theorem, you have to have a right triangle. So then you just construct a right triangle here, and then you see that, oh, this is a 3, 4, 5 triangle, and this must be 5, and then you found that this was 12 too. So in general, whenever you see 90 degrees, always it means Pythagorean theorem. Sometimes you can also split up into multiple components. So we split up areas into multiple components to find the lengths and also. So let's try a problem from the 2014 AMCA. A straight 1 mile stretch of highway, 40 feet wide, is closed. Robert rides his bike on a path of semicircles shown. If he rides at 5 miles an hour, how many hours will it take to cover the 1 mile stretch? Okay, so firstly, since this is 40, right? These parts must be 20. And what does that mean? That means the radius of the semicircle is 20. So these are both going to be 20, the radiuses of the semicircle. So what does that tell us really? Now that we know the radius of the semicircle is going to be 20, that means that, what is the length of the semicircle? So what we can do is we know that this is a 180-degree arc. Semicircle is always a 180-degree arc. So then the length of the arc, semicircle arc, is just going to be 180 over 360 times 2 pi r. So times 2 times 20 times pi. And this is just going to be 1/2 times 40 pi, or 20 pi. So the length of this arc here is going to be equal to 20 pi. But then we see that, okay, Robert's riding his bike on semicircles. Whenever he moves 40 forward, so if Robert moves from here to here, he moves 40 meters forward, 40 feet forward, sorry, 40 feet forward, in order to move that 40 feet forward, he had to actually travel a distance of 20 pi. Because that's when he wants to move 40 feet forward, he had to travel 20 pi distance. But now, he wants to travel 1 mile forward. Okay, so if he wants to travel 1 mile forward, then how much does he actually have to go? Well, they give us in the problem that 1 mile is 5,280 feet. So, in order to travel 5,280 feet, he must be traveling in 5,280 divided by 40 equal to 132 of these semicircular loops. So he's traveling in 132 of these loops. 132 of these semicircular loops. 132 of them. And if he's traveling in 132 of these loops, what is the total distance he must be traveling? Well, if you have 132 loops, and each loop takes 20 pi to travel, this is equal to 2640 pi feet. But then again, we want to find miles per hour. So convert this back to miles. We got this is just going to be equal to pi by 2 miles. Okay, so now we have pi by 2 miles, he must travel, but then we're also given that he travels at 5 miles an hour. So pi by 2 miles divided by 5 is going to equal to the number of hours he must travel, which is pi by 10. This is the answer. Okay, so angle chasing. So angle chasing, there's a lot of theory here. The sum of the angles in a triangle is 180 degrees. A triangle with 2 angles equal will have their corresponding angles equal. And triangles with 2 sides equal will also have their corresponding angles equal. So for example, if we have that these 2 side lengths are equal, then the angles inside must be equal. These angles A must be equal. And similarly, if the 2 angles A are equal, the 2 yellow sides must be equal. So one is true, the other must be true, always. Okay, so, and again, the sum of the angles is always 180 in a triangle. And some more important angle chasing facts. 2 angles are complementary if they sum to 90. So for example, A and B are complementary angles because they sum to 90 degrees. Similarly, 2 angles are supplementary if they sum to 180 degrees. So A and B are supplementary if they sum to 180 degrees. And in general, two lines are supplementary if they're on a line. And intersecting lines, well, in intersecting lines, opposite angles are always equal. So intersecting lines, we have these 2 angles are equal because they're opposite angles. And then we have these 2 angles are equal. And the reason this is true is because, well, A and B are supplementary because they're on a line, right? They're on a line. A and B are supplementary, they're on the line. And similarly, A and B are also, these 2 angles are also supplementary because they're on the line. So that means these 2 angles both must be equal. The same thing for the other two, the same thing for both the B angles. They also must both be equal. And then we also have parallel lines. So in parallel lines, corresponding angles are equal, always. So for example, this angle is going to be equal to this angle because they're corresponding angles. And then we have that the green angles are also going to be equal to this angle because they're intersecting lines. And this green angle is also going to be equal to this green angle because again, they're intersecting lines. Same thing for the B's. These angles are corresponding, and the both angles are equal to this angle and this angle. That gives us some really important facts of angle chasing. There's some more even useful properties. So in a polygon, the angles of a polygon, the sum of the interior angles of a polygon is n minus 2 times 180 degrees if n is the number of sides in the polygon. So for a 10-sided polygon, there's going to be equal to 8 times 180 is equal to 144 with a 0. 1440. And the interior angle of a polygon is just going to be n minus 2 by n times 180. So the reason this is true is because we have n angles, so the interior angle is just going to be this quantity here. And in case you forgot, the reason that this is true is because you can divide an n-sided polygon into n minus 2 triangles, which each have a sum of 180 degrees. So overall, the sum of the angles in the whole polygon is going to be 180 times 4, or 720, in this figure here. And another important fact is the exterior angle of a polygon is 360 by n. This has come useful numerous times before for me. So basically, if you have a polygon and you extend all of this line, this angle is going to be 360 divided by the number of sides. And it's going to be 360 divided by 6 in this case, or 60. And that's the same thing for all the exterior angles. So this will also be 60, this angle will be 60, this angle will also be 60, this will be 60 for all the exterior angles. But then in the octagon here, the exterior angle will just be 360 by 8, which is 45. So this will also be 45, and same thing for all other exterior angles. And another useful table that you might want to know, it can be very useful, especially that it can be very, very useful since you don't have to calculate it every single time. So I'm sure most of you already know that a 3-sided polygon or equilateral triangle has an interior angle of 60, and a 4-sided polygon or square has an interior angle of 90. But some less common ones that are also useful usually are 5, 6, and 8. So 5 has an interior angle of 108, 6 is an interior angle of 120, and 8 is 135. 9 and 10 are optional, you can memorize them if you want, but I haven't seen them come up too often. And some more useful angle tracing properties. So an arc formed by this arc in the center is doubled by the edge. So this arc here is always going to be double of all these arcs. And that works true for anything. So even if you draw something like that, for example, that will also have the same properties. And the reason this is, and also if you have a diameter here, a diameter center, these will all be 90 degrees. If you take any point and connect them to the 2 points on the set, they'll be 90 degrees, always. No matter what, in a diameter. This is also very, very useful. Okay. And I remember seeing an AMC problem a couple of years ago that you were able to solve it using just the basic angle tracing techniques that we discussed here by using isosceles triangles and these tricks here. But then there's a much slicker solution using the inscribed arc fact. You can just do it much faster by using this different fact of arcs. And if you've ever seen any of those polygon problems where they give you a polygon for example, and they ask you, what is the measure of the angle, what is the measure of this angle, for example? This angle is just completely out of place. It doesn't really mean anything. We want to have this angle. And there's a really, really smart solution to solving this that I've always used whenever I've seen these problems. What I do is I draw a circle around this. So I draw a circle that passes through all 8 points of the octagon, the regular octagon. And then, since I drew all 8 points of the octagon, sorry, it's not a very good diagram, so let me just draw a better diagram. So we have a circle, and then we have an octagon inside the circle. Regular octagon inside the circle. And what's special, we want to find this angle. And how we can find this angle is we can see that this angle is going to be half of the arc. It's going to be half of this arc. So by drawing that circle, now we know that this angle is just going to be half of that arc. And what is that arc? The arc is just going to be 3 over 8 times 360. So the arc is going to be 3/8 times 360, which is 135. So this arc is going to be 135, meaning that this angle is going to be 135 divided by 2. And as you can see here, this was just an octagon. It didn't even have a circle anywhere. And we just made a circle around it, and now we can just easily find this angle using the inscribed arc theorem. This inscribed arc theorem is probably one of the most powerful angle tracing theorems ever. So it's very, very important. It can be useful for many, many problems. And also, cyclic quadrilateral has that the sum of the two opposite angles is 180. So some of these will also be 180. And also, what we can do, also another thing by the inscribed arc theorem, where the angle inside the arc is half of it. Oh, and I just want to make it clear that what I mean by inscribed arc is that whenever you have an arc, if you have an arc like this, inscribed arc, meaning that this arc is just going to be a measure of the angle at the very center. So if this arc is 135, the angle at the center is 135. And all the angles that are formed, all these A angles that you see, are going to be half that arc, or half the angle at the center. And that's how this fact also comes true. It's just going to be corollary of the first fact. And in addition, in a cyclic quadrilateral, we have that the sum of opposite angles is 180 degrees. So for example, we also talked about that. Another fact is that if you draw the two diagonals, these two angles are going to be equal, and these two angles are equal since they're in the arc. They're in the same arc. This arc and in this arc. These two angles are in the pink arc, and these two angles are in the green arc. And they're going to be equal. The green angles are equal, the pink angles are equal. So that's why they inscribed arc here. So now let's take a look at three geometry formulas. In a cube, the surface area is 6s squared, the volume is s cubed. In a rectangular prism, the surface area is 2 times the length times the width times the height, times the length times the height. The volume just length times width times height. In a cylinder, the surface area is 2 pi r squared, the sum of the two green faces, plus 2 pi r h, or 2 pi r times r plus h. The volume is r squared pi times h. The surface area of a cone is going to be equal to pi r squared, the area of the bottom face of the cone, plus pi r s, slant, where s is a slant height. And as you can see here, s is marked in the diagram by this. And pi r s is just going to be the circle, sorry, not the circle, the cone when you unwrap it. It's going to be pi r times r plus s. And the volume of cone is going to be 1/3 times r squared times pi h. In a sphere, surface area is 4 pi r squared, the volume is 4 pi r cubed, and there's no really easy way to find it. And also I think one that I forgot to put on here is a prism. The volume of a prism is just going to be equal to the area of the base of the prism times the height. So the area base times the height times 1/3. So 1/3 times the area of the base times the height, which the height is just going to be the perpendicular line. And I'll try to include it on here for the cheat sheet. Sorry, I forgot to include that for now. And there are also many special right triangles and other triangles too. A 45-45-90 triangle has a squared 2 ratio, where these two are both 45 degrees, and these two side lengths are both equal to a. And this is very easily derived by the Pythagorean theorem. And 30-60-90 triangle is that if you have a here, a root 3, a and a root 3 here, and these are both 30 degrees, this is going to be 60 degrees. This side length is going to be a root 3, and this side length is going to be it descends to a, and this side length is 2a. And a lot of people have trouble remember, okay, which side length is going to be a, or which side length is going to be a root 3. So the idea for this here is that the smaller angles, 30-degree angles, always correspond to the smaller side. So the opposite of the 30-degree angle will be the smallest side, and the opposite of the 60-degree angle will be the second longest side, and the opposite of the 90-degree angle will be the longest side. And the way that we get the 30-60-90 triangle ratios is we can actually just construct, we can put another 30-60-90 triangle like this, and then we get an equilateral triangle from here. And then from here, the reason we get an equilateral triangle is then we have, if all these will be 2a, this will be a since it's a bisector. And then from here we see that it's just going to be a root 3 by the Pythagorean theorem. Since this is 90, we see 2a squared minus a squared, the square root of that is going to be a root 3. And as I'm about to just discuss next, the equilateral triangle diagram already drawn there is a 60-60, this is going to be a root 3 here. And this just derives from 30-60-90 triangle properties, or from Pythagorean theorem. Another very special triangle is a 13-14-15 one. A 13-14-15 triangle, if you draw the altitude to the base of the 14 side length, this is going to be 12, and this will be 5, and this will be 9. And And that's just directly by the Pythagorean theorem. And another thing that can be useful to memorize is the area of this is going to be 84, because it's just going to be 5 times 12 divided by 2 plus 12 times 9 divided by 2, which is going to be equal to 84. So you might want to memorize this. Yeah. Also, cube properties. If you have a cube and the side length is a, the diagonal of one of the faces is going to be a root 2, and then because of Pythagorean theorem, and then we can do Pythagorean theorem with a root 2 and a to get a root 3, the space diagonal of the cube. We just use Pythagorean theorem, and this is 90 degrees. And take me here, even though it might not seem like it's 90 degrees, it is, because we can imagine this being a, this being a, this being there. This is going to be square root a square root 2. And this will just be 83 from there. And similar triangles are similar if all angles are the same, or even just two. Because if two angles are the same from the triangles, the third angle must be the same too. Because the sum of the angles in the triangle is 180. And for similar triangles, also, if you see the bases of the triangles are parallel, and the side lengths are in a line, like the figure as you see here, they're also similar. And this can be easily derived from the parallel effect. Because you know that these angles are going to be equal, and then these angles will be equal. And then from there we know that these angles will be equal. So that means these triangles are similar. And in similar triangles, the ratios of all the corresponding side lengths are the same. And the area ratios is just going to be the square of the ratio of the side lengths. So if this is 1, this is 3. The ratio of the areas is just going to be 1 to 9. Now let's take an example problem. In ABC, E is on AB, where AE is 1, and EB is 2. So point D is on AC, such that DE is parallel to BC, so DE is parallel to BC. I'm going to mark on my diagram. These are parallel. And then we also have EF parallel to AC. So let me just get. And then we have EF, the orange side lengths are going to be parallel, and the red side lengths are parallel. Okay, so what does that mean? Well, that means that ADE is going to be similar to ABC. Okay, so what does that mean for us? If AD is similar to ABC, that means the ratios are always going to be the same. And we know the ratio of AE to AB is 1 to 3. Right? Because AE is 1, which is going to be 1, and AB is going to be 1 plus 2, or 3. So if the ratio of AE to AB is 1 to 3, DE over CB is also going to be 1 to 3. But that's actually not relevant for our purposes. So if the area of ABC is x, let's say the area of ABC is equal to x, the whole triangle, ABC. The area of ADE is just going to be 1 over 9 6, or 1/3 squared times x. Because again, the area is the ratio squared proportionality. This is 1 right x. Similarly, for EFB, the triangle to the right, the area ratios, well, EF to CA, well, we know that EB is 2 and AB is 3, so the ratio of the area is just going to be equal to 2/3 squared. So it's going to be 2/3 squared times x, which is 4/9 x. So this will be 4/9 x, meaning that this is going to be 4/9 x. Okay, so now what does that mean for us? Well, the ratio of AC to EF to ABC is clearly just going to be 4/9, since it's going to be 4/9 x over x. And now let me explain. We're actually going to talk about this a little bit later, but now let me explain the way to solve this without actually solving the problem. So let's say you didn't know how to solve the problem, or you were running short on time. How do you solve this? By estimating dimensions. So what you could do is you could see that, okay, ADE is going to be about equal to the area of this triangle I just drew. AD is going to be equal to the purple triangle I just drew, about. And then we can clearly see that EFB is greater than the remaining area here. EFB, the triangle to the right, is going to be greater than this remaining area. Right? Approximately from the diagram. And even though MA says that, oh, the diagrams are drawn to scale, they aren't really necessarily drawn to scale. They're usually drawn pretty close, accurately. So Even if they're not completely accurate, they're usually close at least. Okay, so what does that mean now? That means that the sum of the areas of ADE and EFB is greater than the area of CDEF. And that means that the area of CDEF is going to be less than half the area of ABC. So our answer, the ratio of the areas must be less than 1/2. But then what we notice is that 4/9 is the only option choice that's less than 1/2. And so then we can just mark that as our answer. And this is not the proper way to solve it, of course. The proper way to solve it, I just showed you, was using similar triangles. But if you didn't know how to solve it, or running short on time, you could use this to get an extra free point. Okay, so now let's talk about some test-taking strategies that I mentioned earlier. So in general, you always want to try solving the problem first, before you even try any of these guessing or fake solving strategies. And some other strategies that you can use are substituting the answer choices. So you can substitute answer choices to see which ones will work, and this is also actually useful for checking your work, as we'll discuss later on. And sometimes you can also find patterns with smaller numbers. So you can see, okay, maybe they're all Fibonacci numbers, or maybe they all satisfy some certain pattern. They're all like, so if that problem asks for a large number, you can find patterns with smaller numbers and find the large number. Be like, oh, it must follow the same pattern, maybe you'll find the answer. That's referred to as ingenuous induction. And sometimes, again, you can eliminate some choices. And that means you can maybe narrow it down to one choice to find the solution, or if you can't narrow it down to just one choice, you can still increase your probability of guessing it correct. Right? Because even if you can eliminate 2 or 3 choices, now your probability of guessing it is 50% or 33%. So now you have a much higher chance of getting the problem actually right. And that can help increase your expected score. Okay, so Tom has 12 slips of papers which he wants to put into 5 cutlets. A, B, C, D, and E. So we have 5 cups. A, B, C, D, and E. Okay, so and we want to put the numbers into the cups. So we have to put the sum of the numbers on the slips in each cup to be an integer. So we don't want any fractional parts. We have these decimals, right? We don't want them to be any fractional parts. And furthermore, he wants the 5 integers to be consecutive and increasing from A to E. Okay, so the first step is just to find the sum of all the numbers. And you can actually find the sum of the numbers. I'm not going to waste your time doing that, but if you add all these numbers together, it's not that bad, you get 35. And that means that the numbers that must be consecutive have an average of 35 divided by 5, or 7. So C must be 7, meaning that A and B must be 5 and 6, and D and E must be 8 and 9. And now we have these 5 numbers. We know that the sum of the values in A must be 5, sum of the values in B must be 6, sum of the values in C must be 7, D must be 8, and E must be 9. And you're given that the slip 2 goes into E, so 2 goes into E, and 3 goes into B. And then which one does 3.5 go into? So I'm going to explain 2 solutions to this problem. So first I'm going to show you the way I did this when I first solved the problem. So the way I did this is actually harder. So when I did this was I say, okay, this bucket must sum to 9, so let's just put 2 3.5 values in here. Or you can put 4.5 and 2.5 value. So the idea here is to look at the different possibilities for the possible sums. And what I did is I said, okay, B must be 6, so in order to get a sum of 6, so you must have 2 3s. So the second one must also be 3 here, right? Because that's the only way to get a sum of 6. Because we already have a 3 here, and, right, we use a 3 here. And now we must get another 3, and the only way to get another 3 is by getting a 3 slip inside here. Okay, now with C, now we already used the 3 value. So now we want to somehow fill in the rest of the grid. And we can continue doing this logic by saying that which values could go where. We could look at what could go in 7, and we find that 7 must have 2.5 and 4.5. Because there's no other way to get a sum of 7. 2 plus 5 doesn't work. Or 3 plus 4, sorry, 3 plus 4 would also work. So we could also put 3.4 here. And the way I did is I tried all different cases. And then I found that a certain arrangement would lead to an answer of D. But then there's actually a much easier way of solving it. And solving it is by the process of elimination. Eliminating and narrowing it down to just one possibility. So here's how the quick solution is. So the quick solution is saying, okay, can it go in A? So can the 3.5 slip go into A? If the 3.5 slip goes into A, the next one must be 1.5. But is there any 1.5? No, so this doesn't work. Therefore, we cannot put the 3.5 slip into A. So we've eliminated A, so A doesn't work. What about B? So B, can 3.5 go into B? Of course not, because now if we put 3.5 into B, the total sum is now 6.5. That obviously doesn't work. So B also doesn't work, so you can eliminate B. What about C? If you put 3.5 into C, well, now in order to get a sum of 7, you must put another 3.5 slip, possibly. But there's no other slip, there's only one 3.5 slip. We only have one 3.5 slip. So this won't work. Or we can maybe also put 3.5 and 2.5 are 1, but there's no 1. Or 1.5 and 2, but there's no 1.5. So you can't go to C either, 3.5. So you eliminate C too. Can it go to D? Well, if you put in D, let's do E first. So can it go into E? So if you put into E, now you have a total of 5.5. So then we must put another 3.5 slip here, and same as C actually. Because now we already have a 2, we must create 7 more using 3.5. And the same as C, and that doesn't work, as we found. So therefore we can also eliminate C, E, and then we find that D is the answer. And just to show that it works, if you put 3.5 in D, sorry, I marked it wrong here. So D does not have 3.5 already. I already marked 3.5 here. So if you put 3.5 into D, then you must put a 4.5 here in order to get a sum of 8. And we do have a 4.5. So D, it doesn't need work, D is your answer for this problem. So that's a way of using, this is actually one of the pretty hard problems to solve. But by using a trick, by using the process of elimination, we eliminated A, B, C, and E. And we were left with just D to use. But there's still many more strategies that we can use that I'll talk about. And there's some other guessing strategies that increase your probability of getting them right. And if you can't solve them, here's some tips on guessing. And I don't recommend you try these strategies until you've at least tried the problem for some time. Because sometimes you might be able to solve it. And solving is a 100% guarantee of getting it right. Because guessing, you can still have a pretty good chance of getting it wrong. So again, sometimes you can eliminate option choices to increase your chance of guessing. You can sometimes eliminate too large, too small, you know they're unreasonable, or odd or even, or sometimes maybe something like divisible by 5, or divisible by 6, or so on. In geometry problems, as I'm going to show you right here with this problem, you can estimate the dimensions, estimate the areas, and somehow get a close enough answer. As I also showed an example earlier, where we estimated the area to be correct. And graph paper, rulers, and protractors are allowed. So I highly recommend you bring them so you can try estimating them. Although this year I'm not quite sure how it's going to work out with everything online. And always make sure to mark an answer every problem, of course. So as I said earlier, let's show how to solve this problem without actually solving it. And for the actual proper solution to this problem, you can check out one of the classes I taught earlier. The videos are all available online. And I actually solved this problem using similar triangles. But right now we're going to solve it, assuming you don't know how to solve it. Or you're running out of time. How could you guess the answer and get it right? Or at least have a high chance of getting it right. So what I do here is I say, okay, EFC is approximately equal to the area of EFD. Of course not exactly equal, but it looks about equal. And generally their diagrams are pretty close, if not exactly accurate. Even though they say, but usually they're still at least, if not 100% accurate, they're usually close at least. Okay, so EFD is going to be about EFC, approximately. And then we see that it's also going to be equal to this other triangle here, approximately the areas, right? So, as you can see here, these triangles are all about the same area. About, of course. There's nothing exact here. We're trying to guesstimate the answer right now. And then we see that, okay, if we draw this line, here, this divides into two areas that also seem to be about equal. These seem to be about equal, right? So maybe that this is going to be 1/4. So we said this is maybe a little less than 1/4 AFED. But we're given the area of AFED quadrilateral is 45. And we divide it into 4 triangles that are about the same as area EFC. So EFC is maybe going to have an area of about 10, maybe. So if EFC has an area of about 10, and AFED has an area of about 55, based on the problem, 45, the total area of ADC, the triangle, is going to be 55. So this is going to be 55, the area of this whole triangle. And that means the area of the whole square is going to be about 110. And therefore, we see that answer choices, 108 is the closest. So therefore, 108 is more likely the answer. And it ends up being actually correct. So just by using some simple logic here, by estimating, okay, these are some equal triangle areas that look about equal, and then we drew these other triangles here that look also about equal, or by just using your visual eye and estimating that this is about 1/4 or this is about 1/3 of it, we were finally able to do this. And again, for the proper solution to this problem, the method is not the proper way to solve it. You can check out the proper solution in one of the other classes that I've taught before. And another very important thing to highlight on is to avoid silly mistakes. So after solving a problem, I recommend you reread the question part of the problem to see if your answering is what the questions were asking for. So I've done this many times where I've done everything correct, I've solved all the steps of the problem, and then I just put something different for what the question is actually asking. So maybe if it was asking for fraction over n, I just put m plus n instead of maybe n times n if they were asking for n times n. So make sure to always read what the question is actually asking. Is it asking for the amount of units or of something? Or is it asking for sum of what? Or product of something? So make sure to always read that part, and I've done that myself several times before, so it's not very good. Also, if you're solving the problem and you get an answer that's not any of the option choices, I recommend you check your work, because if your answer is not matching the option choices, it's wrong, of course. So you should probably check your work, see what you did wrong, see if you can try and find your mistake and correct yourself. Another very good strategy is if you see multiple ways to solve the problem, you can use alternate ways to validate your answers. So for example, if there's a combinatorics problem, you could solve it by using both casework and complementary counting, and if the answers match, you're probably correct. So this is a very good way to make sure your answer is correct. Also, another strategy is you can check if your answer is reasonable. So if you get that maybe a car is traveling at 800 miles per hour, that's way too high, so it probably isn't going to be correct. So it's probably not going to be correct in this case. So make sure to utilize all these strategies to hopefully not make some mistakes and hopefully get the most problems possible. Thanks for coming to this class. I hope these tips and strategies were useful and help you on AMCA and other math competitions, and good luck to all of you taking it this year.